Okay, picking up where we left off last time, we were about to talk about the structure of the atom. This is section 2.5 in the text. There are a few sections in the text here and there that we're skipping because even though the topics in those chapters are pretty interesting, and you should definitely read them, we don't have time to cover everything during a summer class. And I won't hold you responsible for anything in the sections that we skip. The schedule for the semester that I put on Blackboard first, before the classes started, reflects the sections that we are leaving out. They're not in there, so you can tell what's going to be covered on tests and quizzes and what's not. I say this because section 2.4 is one of the sections that we left out. So what we did last was actually 2.3. Anyway, section 2.5 is about the structure of the atom. Since all chemistry is essentially based on ultimately atoms, it was inevitable that sooner or later we would have to talk about atoms and specifically how they're set up. As I mentioned, the theory of what atoms were grew up gradually over time. There was a long period of time where scientists didn't even believe that atoms existed. And then around, say, the late 18th, early 19th century, late 17, early 1800s, when they began to suspect that maybe there were such things as atoms, they gradually refined their ideas on how atoms were set up and what was inside them. Dalton's idea of an atom in the early 19th century was that atoms were just really featureless spheres like billiard balls, and that was that. But then from there, we found out a lot more information about them. In the late 19th century, electrons were discovered. By a guy named J.J. Thomson. That is not really extremely important for you to know. But electrons, of course, are extremely important. It was not known, though. Electrons being the negative charged particles. Okay, so Thomson knew that electrons had negative charges, but he did not know where in the atom those negative charges resided. It had long been known that atoms were electrically neutral overall. Even in Dalton's time, that was known. And that's why Dalton postulated that they were just featureless spheres. There was no reason for him at that point to think that there might be positive or negative particles within an atom because they were neutral overall. He didn't stop to think that, maybe there are positive and negative charges in there and there just happen to be the same number. He had no reason to go that far. He just said, well, they're neutral, and so that's all there is. It's just a little sphere. Let's see. So and because Thomson had determined that electrons were negative, that meant that since everybody knew that atoms were electrically neutral overall, there had to be positively charged particles in an atom also. Okay. And he postulated not necessarily that the positive charges were held by separate individual objects like they were with the negative charges, he knew that electrons were separate negatively charged entities, separate from each other. He didn't know that the positive charges were also held by separate individual particles, but he knew that the positive charges had to be there and that the total positive charge had to be equal to the total negative charge. Okay, and so Thomson developed what became known as the plum pudding model. Of the atom. And that was where the negative charged electrons, and these are abbreviations that I use quite frequently, so you better get used to them. Just a negative, when I want to convey that something is negative, I'll use a dash like a negative sign, but I'll circle it to sort of emphasize that it's not just a dash, it's something else. And in this case, that means negative sign. And I do that the same thing with plus signs when I mean it to represent a positive charge. And this means charged. And E minus represents electrons. So negative charged electrons, according to his model, were held in a positively charged sphere. And to him, being British, these reminded him of the raisins in plum pudding. That is plum pudding is a dessert that's not very well known in the US. It's basically like pureed plums with raisins mixed in throughout it. It's one of the, it's in the tradition of, that the British have of using food as a weapon, I think. Along with things like haggis and things like that. But anyway, the book uses the analogy of a blueberry muffin, where the electrons are sort of like the little chunks of blueberry spread throughout the positively charged muffin. And that was the plum pudding model of the atom. It wasn't too long after that that model was superseded by a model that was devised by Ernest Rutherford. In his famous gold foil experiment. And what he did was he took a gold foil and shot positively charged alpha particles, which are actually the nuclei of helium atoms, at a piece of thin gold foil. This, when I say thin, I mean really, really thin. This gold foil was like 1 atom thick. It was so thin. And according to the plum pudding model, though, if you shoot something substantial, like a helium nucleus, at a foil that consists of basically big masses of positively charged, basically a positively charged blob that has a few negative charges mixed in with it, basically these particles that you're shooting at it should all come back at you. Because for one thing, the charges are positive, and the majority of the plum pudding model, at least in terms of space, would also be positively charged. So the charges would repel each other, but also physically, there would be very little space between these spheres within the gold foil, and that leaves very little space for the helium nuclei to get through. What he found was quite different, actually. What he found was that many of the helium nuclei went right through, and many others were deflected. That is, they went through, but they didn't go straight through. And both of these facts were inconsistent with the plum pudding model. And so Rutherford revised the model of the atom into a model where there's the atom is actually mostly empty space. And he also postulated the existence of the nucleus. And that was the nucleus. Okay, so the positive charge is concentrated in a very small area at the center of the atom, and that's known as the nucleus. And that leaves the negative charges to be spread around on the outside somewhere, and the atom is mostly empty space because of how many of those helium particles or helium nuclei went right through. This is known as the nuclear theory of the atom. And in a little more detail, this dates to about 1909, but you don't really need to know the date. In more formal terms, that most of the mass and all of the positive charges in an atom are located in a small core known as the nucleus at the center of the atom. Okay, also, most of the volume of the atom is taken up by literally nothing. But that nothing has tiny negative charges dispersed throughout it. But those negatively charged electrons are really, really tiny compared to the amount of empty space. The amount of space that's devoted to electrons within an atom is really enormous compared to the size of the electrons themselves. So they're widely separated from the nucleus and from each other. Okay, so there's a lot of space even between the electrons themselves. The electrons are negatively charged, which means they repel each other, so you would expect there to be a lot of space between them. Okay. And any given atom will have the same number of positive charges and negative charges. Which makes the atom neutral overall, electrically neutral. And this was a big step forward in the model of the atom. We're getting much closer to what it's really like, or, well, at least according to our current understanding, than was the case before. But one thing it didn't account for was the fact that it is possible, and it was known by this time, that some atoms of the same element could have different masses. And that's because neutrons hadn't been discovered yet. And of course, when you have two atoms of the same element that have different masses, what you've really got are what are now known as isotopes. And isotopes have different masses because they have different numbers of neutrons. But they didn't know about neutrons yet. So he kind of missed that. The neutron, in terms of mass, is about the same as a proton. But a neutron, as the name implies, is electrically neutral, has no charge. So if you change the number of neutrons, you change the mass of an atom, but because it has no electrical charge, it doesn't really change the chemical properties any. Okay, so in reality, we now know that the nucleus has something like 99.9% of the mass of an atom, but a very small proportion of its overall volume. It's been said, I think that, let's see, I'm trying to remember the exact sizes, but it's been said that basically if the nucleus of an atom were the size of a baseball, then the nearest electrons would be something like 100 yards away. And so that gives you kind of an idea of how much empty space there is within an atom. Okay. Basically, the nucleus is extremely dense. If you calculate the density of the nucleus of a typical atom, you come up with a number that's pretty similar to the densities of black holes, you know, which are just monumental densities, that are just kind of unbelievably big, you know, for the amount of mass that's crammed into each, say, cubic centimeter of space. But that huge density in the nucleus only makes up a very small proportion of the overall volume of the atom. Atoms are so small that we as human beings only experience them at a very large level. So we really only notice the properties of atoms overall when there are lots of them together. And so we're kind of, what we experience is sort of the overall average properties of the atoms. And so when you take that extremely dense nucleus and average it together with all of that empty space where the density is essentially zero, what you end up for the entire atom with is a density that's basically the densities of things that we're used to every day, you know, like paper or plastic or things like that. So it's kind of lucky that there's that much empty space within an atom. Otherwise, everything would be as dense as a black hole, and you know, things would be extremely heavy, and I guess we'd have to be really, really strong to deal with it. Anyway, so now that we're getting close to the real, or what we think of today as the real structure of the atom, we can start talking about the subatomic particles. The subatomic particles of course, are protons, neutrons, and electrons. The protons and electrons, as I said, were discovered in the late 19th century. Neutrons were not discovered until, I believe it was the 1930s or maybe even the 1940s when work on the Manhattan Project basically started. The neutrons were a pretty recent discovery then. And so that they were the last part, or the last major part of the atom that was discovered. And as abbreviations, I'm just sometimes going to use P for protons, N for neutrons, and E minus for electrons. So all atoms, as it turns out, are made up of protons, neutrons, and electrons. And they're always in the same relative positions. So protons and neutrons in the nucleus and electrons around the nucleus. Okay, but there's, of course, a wide variety of characteristics to matter. Even though all matter is made up of atoms with the same particles in the same relative locations, the wide differences that we observe from one type of matter to another are due entirely to the different numbers of protons, neutrons, and electrons in the atoms that make up that matter. Just having the same particles in different proportions can mean a pretty enormous difference in the chemical and physical properties of atoms. Okay, the protons and neutrons are in the nucleus, and they have similar masses. The proton has a mass of 1.67262 times 10 to the minus 27 kilograms. And that's equal to, in terms of atomic mass units, it's about 1 atomic mass unit, but to be exact, it's 1.00727 AMU. But for most purposes, we call it 1. The neutron, on the other hand, has a mass that's almost the same, but just a little bit different from the proton. That's 1.67493 times 10 to the minus 27 kilograms, or 1.00866 AMUs. But again, for most purposes, we can call that 1 AMU. So we don't really have to go any further than that most of the time. Notice how small these masses are. 10 to the minus 27 kilograms, I mean, that's kind of unbelievably small on a human scale. A kilogram is about 2 pounds. And so you can think of that in terms of pounds. It's going to be really, really small. But it's actually a pretty big mass on the scale of atoms, because atoms are really, really, really tiny. Okay. The proton, of course, has a charge of +1. And the neutron has a charge of 0. Now, to look at electrons, Electrons, first of all, of course, are outside the nucleus. We'll get in more detail into exactly how the electrons are arranged later. For now, we'll just say that the electrons are in orbits around the nucleus. And they're widely spaced. This is how atoms end up being mostly empty space, because there's so much space between the electrons. The mass is equal to to put it on the scale of 10 to the minus 27 kilograms, like we were using for the protons and neutrons, it's 0.00091 times 10 to the minus 27 kilograms. In proper scientific notation, that's 9.1 times 10 to the minus 31 kilograms. And that's about 0.00055 AMUs, atomic mass units. So compared to the masses for, say, a neutron or a proton, you can see that electrons are really, really tiny. The electrical charge is -1. We want to talk about the charges in a little more detail. Whoops. We see that, let's see here, charges of the charges of protons and electrons are equal in magnitude, but opposite in sign. So in other words, one proton cancels out one electron, I mean. And vice versa. One electron cancels out one proton. And again, that's how atoms end up having a neutral charge overall. For most purposes, we just call the charge on a proton +1 for simplicity. But the SI unit for electrical charge is the coulomb. And in coulombs, the charge on a proton would be plus 1.60218 times 10 to the minus 19 coulombs. You don't have to know that number. You can look it up if you need it. And actually, the same goes for the exact mass of protons and neutrons and electrons. If you need a mass for a proton, well, the only mass for a proton and neutron that you should remember would be one atomic mass unit for each of them. For the electrons, for that matter, you don't even have to remember the atomic mass unit number. Just remember that it's really, really small. For the charges, the only charge that you really need to remember is +1 for a proton and -1 for an electron. This number you can look up if you need it. So the charge on an electron, we usually just call -1. But in terms of coulombs, it's the same as a proton, only negative instead of positive. Okay, oh, and one thing that I haven't done is draw an approximate picture of an atom. Most people have probably seen this before. This is a very simplified model, and we'll add a lot of complexity to it later. But for an atom, you normally have the nucleus. And then around the outside, in more or less spherical orbits, less in my case, you have electrons. So that's kind of the model that we're working with at this point. Okay. Looking at a little more detail in some of these subatomic particles. It turns out that the way we define an element is actually by the number of protons. Okay. It turns out the number of protons is also known as the atomic number, and the symbol for atomic number is a capital Z. And we'll say a little bit more about this in a moment, but I think it's about time to end the first segment of the video. So I'll be right back.